Now I would like to talk about how we represent fractions. Okay, representing fractions. So far I talked about unsigned integers. So let us talk about fractions. Now you can represent a fraction, okay, in binary. The same way that you can represent a fraction in decimal, you can also represent a fraction in binary or in any number system. Okay, so we use the position of the digit inside the number to specify the weight of that digit. So if you have a number n and radix r, it can also have a fraction part. So I can write it like this. So you can see that the integer part appears before the point. Now this is what I call it the radix point. Okay. In decimal, we call it the decimal point. In binary, we call it the binary point. And the rest here will be the fraction. So we write the integer part, then we write the dot or the point, and then after that we write the fraction. So remember to use the dot. Okay, we don't use the comma like we do in French or Arabic. We use the comma to specify the fraction. No, we use the dot. So make sure in the exam or the quiz, you make sure that you write the dot. Okay, and everything after the dot will be the fraction. Okay, is this clear? Understood? Now, okay. So please make sure that you use the dot. So d minus 1 here indicates the first digit in the fraction. D minus 2 will be the second digit in the fraction. And D minus M, it will be the M digit in the fraction. So notice that I'm using minus 1, minus 2, and minus M. I'm using here a negative position. And the reason why, because these digits exist in the fraction. Whereas in the case of the integer part, we start from 0, 1 up to n minus 1 when we have n digits in the integer part. But in the case of the fraction, we start with negative 1, negative 2. So this indicates the position of the digit in the fraction. And we can use this to specify the weight. Okay, so this is the integer part, this is the fraction part, and this is what we call the radix point. If this was decimal, it will be the decimal point. If it was binary, we call it the binary point. Okay, so it separates the integer part from the fraction part. Now we can always write the value, okay, of the number n in radix r. So in the case of the integer part, we start here at d0 is the least significant digit. d1 will be multiplied by r, d2 will be multiplied by r squared, and so on. In the case of the fraction, we take d minus 1. This is the first digit after the point. It's multiplied by r to the power negative 1. In other words, we are dividing d by r. D minus 1 is divided by r. R to the power minus 1 is division by r. So I'm using a negative exponent. Okay, so when you multiply by r to the power negative 1, it's the same thing as division by r. D minus 2, that will be the second digit in the fraction part. It's multiplied by r raised to the power negative 2. So we are dividing by r squared, and so on. So the last digit in the fraction here, d minus m, is multiplied by r to the power negative m. For example, if this actually number was in decimal, then r will be 10. The radix will be 10. So the first digit in the fraction will be divided by 10. The second one will be divided by 100, and so on. Okay? If this were in binary, then r will be 2. So it will be 2 to the power negative 1, 2 to the power negative 2, and so on. So we can write it in sigma notation as a summation. This is the integer part. I here is the index, or if you would like, the position of the digit. So I starts from 0 to n minus 1 di here. These are the digits that exist in the integer part. We multiply them by r to the power I. And then this is the second summation here, okay, which is written in sigma notation. It's for the fraction part. So dj here is the digit in the fraction. I'm using here j from minus 1 to negative m. Of course, here negative m will be the smaller value, negative 1 will be the larger value, so I'm writing them in this order. Anyway, it will be dj multiplied by r to the power j, but the exponent here is negative, indicating the fraction part. I have examples about how to represent fractions. Here's an example in decimal. Okay, so you can see the number here is 2,409.87. Now this 2 is multiplied by 1,000, 10 to the power 3. This 4 is multiplied by 100. This 0 is multiplied by 10, but 0 multiplied by 10 is 0, so I'm not showing it. This 9 is multiplied by 1. Now this 8 is divided by 10. This is actually in the fraction. So I'm multiplying it by 10 to the power negative 1, and this 7 is divided by 100. So this is why I'm multiplying it by 10 to the power negative 2. Okay? So here's an example of a number which is in decimal. I can do exactly the same way in other radices and other number systems. For example, in binary. In binary, we only have 2 digits. So you can see that this one is what? This one here, the most significant one is what? Can anyone answer this question? Let me use here my highlighter.
1 multiplied by 10.
1 multiplied by 2 to the power 3.
See, this is 2, right? Radix
Yes.
2. So this one is what?
Multiplied by 2 to the power 3. 1 to the power.
Which is what?
8.
8.
Yes.
So this one is 8. This one is what?
4.
4.
This one is what?
2.
0 and 2.
1.
It is
13.
just
1.
1.
1. Yes.
We have here 0 multiplied by 2. This is just 1 multiplied by 1 is just 1. How about this one?
1 over
It's
Divided by
minus
1.
1 over 2.
It's half. Yes, it's
1
1
over 2.
divided by 2. How about this one?
1 over 8.
No, this is 1 over 2, 1 over 4, 1 over 8. This must be what?
1 over 16.
1 over 16, exactly.
Yeah.
So all what you have to do is just add the weights. And if you add the weights, this is actually 2 to the power 3. This is 8. This is 4. This is 1. This is half. This is 1 over 16. You get 13.5625. So the decimal value of this binary number is 13.5625. Is this clear?
So after the binary digit, we start from minus 1, not from 0.
So the fraction, the first digit after the binary point will be the first digit in the fraction. It will have the weight -1.
Okay.
2 to the power -1. Then yes, so 2 to the power 0 is for the integer part. So the digit 0 is here.
Yes.
The fraction we start with -1. Yes, we start with -1.
Okay.
I have more examples. Let us take a look at this one. So this 7 here is multiplied by what?
By 8 to the power 2.
Yes, by 8 squared, which is 64. So we have to multiply 7 by 64. This 3 is what?
3.
It is just 3. It's unit, right?
Yes.
How about actually this 6?
6 over 8.
6 over 8.
6 over 8. How about this 4?
4
4
over
over 64.
64. Yes.
Yes, we divide by 64. Or we multiply by 8 to the power -2.
Yes.
So if you do the math, you get 451.8125. So you can always convert from any number system, okay, from binary, from octal, from hexadecimal. It does not really matter, to decimal, using just the equation that we have seen in the previous slide. I have more examples. Let us take a look at this one. This is hexadecimal. So what is A?
10.
10.
10 multiplied by what?
10 multiplied by 16 to the 3.
16 to the power 2.
To the
2
power 2.
or 3?
Yes.
2
Two,
or
two.
3? 2, yes,
Two.
because we start here at 0. Okay.
Yes.
So this A here must be multiplied by 16 squared. 16 squared is 256. Now this one is multiplied by what?
16 to the
16.
1, so 16.
16. And this F is what?
Just 15.
Now this 8 is what?
8 over 16.
Yes, 8 over 16, which is just half. So if you do the math, you get 2,591.5. That's the decimal value of this hexadecimal number. So you can see that numbers can have a fraction. Okay, they can have a fraction. I also have more examples. How about this one? Now you see that here I'm using radix 5. Although radix 5 is not really common, what is common is actually decimal and binary. And we have seen that octal and hexadecimal are related to binary because 8 is 2 to the power 3 and 16 is 2 to the power 4. But 5 really is not related, okay? But This is just an example to illustrate how we can do the conversion. So it does not really matter. You can choose whatever radix you want. So this 4 is multiplied by what?
25.
By
to the
5
power,
to the 2.
2.
5 squared, right? Which is 25. How about this 2?
10 multiplied by 5.
Yes, and this 3?
3.
Only 3.
3,
It is
yes.
3. How about this one?
1
1
over
over
5.
5.
1 over 5, which is 0.2. So if you do the math, you get 113.2. About this number?
So multiply
Can you
6 to the 2.
Okay, so it's 2 multiplied by what?
By 6 to the 2.
6 power to 4.
6 squared, right?
6 squared.
Yeah.
Okay.
Okay, then what?
Then 6 multiplied by 6,
By
which is
6.
36.
6
And
multiplied
then
by
3.
6.
Can it be
And-
6?
Is this number allowed?
No,
Doctor.
it can't be 6.
Can we have
Because-
digit 6 in radix 6?
No, R minus
No,
1.
no, no.
Exactly. So this digit should not exist. So therefore, this number is wrong. In other words, this is a trick. Okay, if you get something like this in the exam, don't convert it. Write that this number cannot exist in radix 6 because the digit 6 does not exist. The largest digit that you can have in radix 6 is 5. You can have from 0 to 5, but not 6. So this number is illegal. Okay, it cannot exist. It's a wrong number. Okay, it's you cannot really have the digit 6. So digit 6 is not allowed in radix 6. Okay, this is actually just an example to illustrate that. Okay, that you should not really write such numbers. Okay, let us move on. Now, how about if I would like to convert a decimal fraction to binary? How do I convert a decimal fraction to
By
binary?
2.
To radix? Hmm?
Multiply by 2.
Oh, yes. If it were an integer, I would divide by 2. But because it's a fraction, I'm going to multiply it by 2. Exactly. So what the solution is to multiply n by 2 repeatedly and collect the integer bits. So for example, when I multiply 0.6875 by 2, I get 1.375. So this one here is the first bit that appears in the fraction. That will be the first fraction bit. Now we take the new fraction, which is 0.375, and multiply it again by 2. We get 0.75. So the 0 here, fraction. We take the 0.75 and multiply it by 2, we get 1.5. So this one here is my third fraction bit. Now we take only the fraction, which is 0.5 multiplied by 2, we get 1.0. So this one will be my fourth fraction bit. But now the new fraction is 0.0, so stop when the new fraction is 0.0. So this is the first fraction bit, this is the last fraction bit, and we stop when the new fraction is equal to 0.0. Now sometimes, because it's a fraction, unlike integers actually conversion will always stop. But in the case of a fraction, this might go forever. Yani you might actually have an infinite number of bits in the fraction. So we stop when we have enough fraction bits. Sometimes I only need, let us say, 10 fraction bits or 20 fraction bits. So there is no need to continue forever. Yani there are examples in which this conversion procedure does not end. So you terminate when you have sufficient fraction bits. So
And how will you decide?
So in this example, 0.6875 is equal to 0.1011 in binary. If you would like converted back from binary to decimal, you will get exactly 0.875. This one will be 1 over 2. Here we have 0 over 4. Here I have 1 over 8. Here I have 1 over 16. If you add half plus 1 over 4 plus 1 over 16, you will get 0.6875. As I said, that this procedure might not terminate. So therefore, the question will tell you, you will get an approximation, not an exact fraction, because fractions, okay, might actually go forever. Okay, so some numbers cannot be represented exactly in binary as a fraction. not as an integer. Integers can be represented exactly, but fractions might not be represented exactly in binary. So we stop when we have sufficient number of fraction bits. Is this clear? Someone had a question.
Yes, it's clear, doctor. But my question was, how will I decide when to terminate or when to stop?
Well,
and
the
how
question
I
has
know?
to, okay, so that actually depends on how many bits you would like to store in the fraction. Okay, so for example, numbers that are that have fractions that you would like to represent will have a specific number of bits in the fraction, depending, of course, on the amount of memory that you would like to use for the number. So if you are using a specific number of bits, then you stop when this number of bits have been reached. Okay.
Okay.
So
And,
this has to be specified in the problem itself, in the problem statement. Or when you reach 0.0, if the new fraction becomes 0.0, then there is no need to continue because all the remaining bits in the fraction will be all zeros. And you can actually write here infinite number of zeros in the fraction. It does not really change the fraction.
Yeah, that's obvious.
Okay.
Doctor,
Yeah.
Yes, Fadda.
what if the number is 25.6875?
Okay, I'll talk about this. You convert the integer part separately and the fraction part separately. I have an example about this. Let us continue.
One more observation, doctor, if you may.
Yes.
For the fraction side, the numbering or the most significant will be from up to down, not like
right. So we go from
right?
left to right. We go from left to right. So therefore, the first bit that we have discovered is the first bit after the binary point.
Okay.
So we start here from
the
left,
integer.
unlike the integer. From actually the integer, we go from right to left.
Okay.
Yes, it's a good observation. Yes, it's true. If you want, you can always verify that your conversion was done properly. Take the fraction in binary, which is 0.1011, and then convert it back to decimal and see if you get 0.6875. Okay?
Yes, okay. Thank you.
Now, you can actually do this in any radix R. Yani if you have, for example, in number n, okay, and you would like to convert it, okay, to a fraction to a radix R, what you have to do, what we have done in the previous slide is that we converted to binary, which is radix 2. So we multiplied by 2. But if you would like to convert it to radix R, okay, what you have to do is that you have to discover d minus 1, d minus 2, d minus, all the way here to d minus m, but these are in radix R. So rather than multiplying n by 2, we multiply it by r. R is the radix, okay? We multiply n by r, and we continue here. So when we multiply n by r, I discover d minus 1. Because if you multiply everything here by r, so r minus 1 multiplied by r will give you d minus 1. Now here d minus 2 will be multiplied. This was r minus 2 multiplied by r becomes r minus 1 and so on. So d minus 1 here will be the first digit, okay, in radix r appearing in the fraction, okay? So it will be the first digit, okay, in the fraction appearing in the in radix r, and then we take the fractional part and then we repeat to obtain d minus 2, d minus 3, and so on. And we stop when the new fraction becomes 0.0 or when we have sufficient fraction digits, because this procedure might not terminate, okay? Let me show you more examples. Okay, these are more conversion examples. Suppose I would like to convert to octal. So this number here is in decimal, 139.6875, and I would like to convert it to octal. How do I do this?
Convert the integers alone and the decimals alone. The integers, you will divide them by 8, and the decimals, you'll multiply them by
fraction. The fraction, we call it the fraction. What appears after the decimal point, we call it the fraction, yes. So the fractional part, we convert it to what?
Convert it to multiply them by 8.
We multiply it by 8, yes, correct. So let us do this. So yes, so we're going to split n into 139 plus the fraction, which is 0.6875. So each one will be converted separately. And then we are going to join the integer and the fraction later. So let us take here 139 and convert it. So we divide by 8. In the case of the fraction, we multiply by 8. Okay, so this is the procedure. So we take 139 divide by 8, I get 17 point something. But if you multiply 8 by 17, okay, if you multiply 8 by 17, anyone has a calculator? 8 multiplied by 17?
136.
Exactly. So 139 minus 136, you get the remainder, which is 3. Okay. So this is the integer remainder. This is called integer division. So we don't write it as 17 point. We write just 17 as the quotient, and the remainder is 3. Now notice that 3, this is actually is what? It's digit 0, okay, in the integer part. Now we take the quotient, which is 17, and then I divide again by 8. Now 17 divided by 8, we get 2 point something. 16 divided by 8 is 2. But there is a remainder, which is 1. Okay, so 17 minus the 16 will give you the remainder, which is 1. Now 2 now is less than 8. So when you divide 2 by 8, you get 0, and the remainder is the 2. Now this procedure is going to stop. We always stop when the quotient is equal to 0. That's it. So therefore, 139 is 213 in octal. Okay. Now what we have to do is that we have to do the fraction part. So we are going to take the 0.6875 and multiply it by 8. Now when we multiply it by 8, we get 5.5. Now 5 here is my first digit in the fraction. We take the 0.5 and multiply it again by 8, we get 4.0. So 4 is my second digit in the fraction. Now the remaining, so the new fraction now becomes 0.0. So we stop when the new fraction becomes 0.0. If the fraction is not really 0.0, then in this case, we have to continue multiplying by 8 until we reach 0.0, or we have sufficient digits in the fraction. So now we can join them. So 139 is 213 in octal. Notice that the 3 here is digit 0. Then we have the 1, then the 2. So it's actually from right to left, whereas the fraction, which is 0.6875, is 0.54. So the 5 here is the first digit that appears after the radix point. Then we have the 4. You can always verify that. You can always check that. All what we have to do now is to join them. So 139.6875 will be 213.54 in octal. Is this clear? So this is an example about how we convert a decimal to octal. Right. If I'm not receiving question, yes, go ahead.
What's the R in radix stands for?
It means R here is 8.
Oh, it's like any number, right?
So when I'm talking about octal, the R is 8. If I'm talking about binary, R is 2. If I'm talking about decimal, R is 10. That's the meaning of R.
Okay.
R is the radix. Okay.
It's the highest number you can use plus 1.
Well, it's actually the digits will be, in the case of radix 8, the digits will be from 0 to 7. We have seen that in a previous slide. If you are using radix R, then you can go from 0 to R minus 1. These are the digits. So when the radix is 2, we go 0 and 1. Decimal, we go from 0 to 9. That's what it means. Okay.
Okay.
So this is the conversion procedure that I just mentioned in the we have seen in the previous slide. So if you have a decimal number n and you would like to convert it to any radix r, we did it actually to binary, so the radix was 2. We did it to octal, so the radix was 8. So what we have to do is that we have to convert the integer part separately, and then we have to convert the fraction part. In order to convert the integer part, we have to divide. We divide n by r, the radix. And if we are converting to binary, we divide by 2. If I'm actually converting to octal, I divide by 8. If I'm actually converting to hexadecimal, I divide by 16. Okay? And then we look at the remainders. And we get the remainders in reverse order. So we obtain digit 0, then digit 1, then digit 2. So basically, we are obtaining them from right to left. This is for the integer part. In the case of the fractional part, we multiply, okay, the fraction by r, by the radix r. So if it is binary, we multiply by 2. If I would like to convert it to binary, I multiply by 2. If I would like to convert it to octal, I multiply by 8, and so on. And then finally, we just join the result. We join the integer part with the fractional. This is the conversion procedure. It's simple. It's not really that difficult. You just need to practice this. There are many exercises at the end of chapter 1. So go to your textbook and to the chapter and do these exercises and look at their solutions. Okay, they are available in the appendix. Okay. Right. Yes, go ahead. Go ahead.
Where is available?
In your textbook, at the end of the chapter, inside the chapter, there are many examples. You can actually just look at these examples and look at their solution, and then go to the exercises at the end of the chapter. I'm going to actually post many exercises. If you, I'm right now revising the web page for the course. It's available on my website. I'm going to list many exercises for you to practice. So you can actually practice doing these exercises, and you can look at their solution in the textbook in the appendix. Okay. So I'm going to have a link from Blackboard to my to the course web page, and you will find a lot of information. Okay, where you actually can find exercises for you to practice. Is this clear?
Yes, thank you.
Right.
Yes.
So now, sometimes if you would like to convert between binary, octal, and hexadecimal, the procedure can be simplified. Okay, so you don't really have to do what we have seen in the previous slide. So rather than dividing and multiplying, what you can do is that you can start grouping, because binary, octal, and hexadecimal are related. So remember that octal is radix 8, and 8 is 2 to the power 3. So it's related to binary. So I can actually take a group of 3 bits, okay, in binary and convert it to octal. Hexadecimal is radix 16. 16 is 2 to the power 4. It's related to binary. So I take a group of 4 bits and convert it to hexadecimal. So the procedure can be simplified. The conversion procedure can be simplified. So we can start at the radix point. We can convert the integer part starting from the right, and we can move to the left. And then we can convert the fractional part starting from the left and moving to the right. Starting from the first bit after the fraction, after the radix point, and then we can move to the right. Let us take a look at this example. Now notice that this number is in binary, okay? It's a binary number. Notice that this is the binary point. Anything which is to the left of this binary point is the integer part. Everything which appears to the right is the fraction. Clear? Is this clear? Now,
Yes.
I'm going to convert this to octal. I'm going to convert this to hexadecimal. So in the case of octal, we look at groups of 3 bits. So we start at the binary point and we go to the left, okay, for the integer part. We start at the binary point and we move to the right in the case of the fraction part. Okay, so for the integer is right to left. So we start here at 0, 1, 1, right? That's actually, this is a group of 3 bits. It will be 3. Next, we have 0, 0, 1. What is 0, 0, 1? It's just 1.
1.
Yes. 1. Next, we have 1, 1, 0.
3.
5.
1, 1, 0.
6.
6. Yeah, thank you. 6. 0, 1, 0.
2.
And then 1, 1, 1.
7.
7. Good. Let us do it now for the fraction. In the case of the fraction, I'm going to start at the binary point and move to the right. 0, 1, 0.
1 over 2.
Just just convert it to a digit.
2.
It's just 2. So the fraction will go from left to right. So 2. Then I have 1, 0, 0.
4.
Okay, good. 1, 1, 1.
7.
And 1, 0, 0, 0. 1, 0, 0.
1.
1, 0, 0.
1.
4.
4.
Yeah, 4. This is 4. And then we have 1, 0, 1.
5.
Now here I have 0, 1.
1.
We can add 0.
1.
Well, 0, 1 is just 2 bits. I need 3 bits. I need 3 bits. So therefore, we have to insert a 0 in the fraction. So whatever actually here is not really shown in binary, you can always insert zeros in the fraction. It does not really change anything in the fraction, right? So in the case of a fraction, you can always insert zeros to the right. In the case of the integer, you can always insert zeros from the left. So for this reason, we need 3 bits. So this is 0, 1, 0. It's not actually 0, 1. It's 0, 1, 0. So what is 0, 1, 0?
2.
Oh, this is 2. It's not a 1.
Yes.
Okay. It's a 2. It's 0, 1, 0. We have to add a third bit here, which is a 0. So this is 0, 1, 0. It's a 2. So you have to be very careful about the fraction when you convert it from binary to octal. Let us repeat. Let us do it actually from binary to hexadecimal. Okay. So what I'm going to do now is I'm going to use here my eraser. I'm going to erase here these shown, okay, the highlighter, and repeat everything and do it in hexadecimal. So how do I convert from binary to hexadecimal?
Take 4 bits.
A group of 4 bits. Yes, group of 4 bits. So let me use my highlighter again. Now, 4 bits, it will be 1011. What is 1011?
B.
Yes, it's 11. It's B. Then we have 1000.
8.
No. 1000.
10.
Did you say A?
8. I said
8. Ah,
Yes,
8. The number 8. Yes.
Yes.
1. Okay, 8. Okay. So how about 0101?
5.
Now I only have 3 bits here, 111, but I need actually 1 more bit. So we
Add a
can
0 to the left.
we can insert a 0, right?
Added. Yeah.
So what do we get?
7.
7.
Excellent. That. Now let us do it from the for the fractional part. Okay, this is the fraction. So 0101.
5.
5.
Excellent. How about 0011?
3.
3.
1100?
3.
Again, I cannot hear you.
6.
C, it's 12. C.
Yes.
How about 1010?
A.
Okay, now I'm left with just 1.
3
You
0.
can put right side zeros.
Yes. It will be
B.
what?
8.
8. It will be 8. Yes. Yes. So this is actually how I do the conversion. Is this clear?
Yes.
Clear.
Excellent. So now we understand actually how we can convert between binary and octal and binary and hexadecimal. If I would like to convert from octal to hexadecimal directly, I can actually go from octal to binary and then from binary to hexadecimal, and vice versa. If I would like to go from hexadecimal to octal, I can go to binary first and then I can go to octal. Okay? Clear? Is this clear?
Yes, clear.
Could you repeat the last point?
So if I would like to go from octal to hexadecimal, I have to go through binary.
Yes, I get it. Yeah.
Okay. So if the binary is not given, if the octal is given, and I would like to actually convert to hexadecimal, convert from octal to binary first, and then convert the binary to hexadecimal, and vice versa. If you'd like to go from hexadecimal to octal, go through binary first and then to octal.
Yes, thank you.
Okay, very good. Now let me conclude with some important properties of fraction. I'm running out of time. How many fractional values exist with m fraction bits? If you use m bits in the fraction, how many values? Any answer? Each bit can be 0 or 1. So there are 2 values for each bit, and we have m bits in the fraction. So how many possible fractional values? How many values can you have with m bits?
M over 2?
No, these are just actually bits. So you can,
minus m.
so each bit can be 2 values, right? So if you use m bits in the fraction, how many values can you have?
2 power m.
2m.
2 to the power m, yes. but these actually are fractional values, okay? Like in the case of integer, if you use m bits in the integer, you can have 2 to the power m integer values. If you use m bits in the fraction, you will have 2 to the power m fractional
minus
values. Well, no, we don't. We are just actually counting in total how many fractions we have, okay? We are not saying actually what's the smallest value and the largest value. We are talking in total, okay? So 2 to the power m fractions. Now, here's the question. What is the largest fraction value if you use m bits?
2 to the power m minus 1.
Well, that's not an integer. That's a fraction. So 0.1111, if you use m ones, what's the value of this? Let me give you, let me do it in decimal. If I use the 3 digits in decimal, or let us say just 2 digits in decimal, 0.99, what's the value? 0.99. How can you root? So what is the value of 0.99? You can actually, what's the largest fraction if you use it in decimal? 0.99. It's actually 1 minus 0.01. It's actually 1 minus 10 to the power negative 2. So if you write it the largest fraction, okay, value, okay, so you have m bits in binary. It's 0.1111. You have m ones. So it will be 2 to the power minus 1 plus 2 to the power negative 2 plus all the way 2 to the power minus m. Now the value of this number, okay, this is a fraction, okay, it's less than 1. It is 1 minus 2 to the power 2 to the power negative m. Because if you add 2 to the power negative m to this number, you will get exactly 1. Okay, so it's slightly less than 1. It's like 0.9999, so many nines in decimal. So if you add 2 to the power negative m to the number, you get exactly 1. So let me say in general, okay, the largest, okay, fraction value, if you use m fraction digits in radix r, it will be 1 minus r to the power negative m. Because if you add r to the power negative m to this value, so it's r to the power negative 1 plus r to the power negative 2 and so on, plus r to the power negative m, so it will be 1 minus r to the power minus m. It's slightly less than 1, okay? It's very close to 1, but not exactly equal to 1. So for example, if you use it for decimal, it will be 1 minus 10 to the power negative m. If you use it in binary, it's 1 minus 2 to the power negative m. If you use it in hexadecimal, it will be 1 minus 16 to the power minus. I'm running out of time, so that's it for today. Let me actually pause here. Okay, so let me just stop the recording. Okay, very good. Type. So today's lecture will be about binary codes. Last time I talked about fractions, how we can represent fractions in binary. We have seen also how we can convert actually fractions. We can convert them actually between different number systems, between binary, decimal, octal, and hexadecimal. But we can also use other number systems if you want. We can change the base or the radix. Today, I would like to talk about a new topic, which is about binary codes. Okay, so we have seen numbers, okay, how we can represent numbers in different number systems. But how about things like characters, colors? How do we represent them? The way to do this, remember that the computer system is a digital system. So we have to represent everything as digits, as numbers. So in order to represent characters and colors, we have to represent them with numbers, okay, with digits. So we define a set of all the elements that should be represented, and we assign a unique binary code to each element of the set. So it depends on how many elements I would like to represent, and we have to decide on the number of bits. Since everything is represented in binary, we have to decide that how many bits in binary we need for these elements that we have in this set. So if we have n bits, we can represent 2 to the power n values, okay, with let me use here my highlighter. So if we use n bits, okay, in binary, then we can have 2 to the power n, the number of values, okay, that we can represent in binary. And if each element in the set is represented uniquely with a binary number, we can represent 2 to the power n values or elements in the set. So, so this is called coding, okay? So we can assign a code to each element in the set. So for example, if we are dealing with characters, we can assign to each character, we can assign it a code. If we are dealing with, let us say, colors, we can assign to each color, we can assign to it a code. So this is how we can deal with non-numeric data. We can also do coding for decimal numbers, for decimal digits. We can also use the same idea, the same technique to represent decimal digits. I will also talk about this. Let me start first with non-numeric data. Okay, so suppose I would like to represent colors. If I would like to represent colors, let us say I would like to represent them with codes. Suppose I would like to deal with the colors of the rainbow. So there are 7 colors of the rainbow. So the question, how many bits do we need to represent the 7 colors of the rainbow? So we need 7 values, okay? So 7 codes. So how many bits do I need to represent 7 codes? This is the question. Now, if I use 2 bits, how many values we can have with 2 bits? If we use 2 bits, how many values can we have?
4.
This is the question to you. 4. 2 to the power 2 is equal to 4. Exactly. If I use 4 bits, how many values can I have in binary if I use 4 bits?
16.
16. Exactly. 16. Now, 16 probably might be too much. Okay, 4 bits. We don't need 4 bits to code the 7 colors. If we use 3 bits, how many values can we have with 3 bits?
8.
8, exactly. So 8 might be reasonable. Okay, so we need more than 7. Well, at least 7. At least we need 7 unique values. So if I use 8, okay, that will be good because I can actually have a unique value, a unique code, okay, for each one of these 7 colors. If I use 4 bits, I will have 16, okay, but that will be too many. If I use, let us say, 2 bits, I will only have 4 possible codes, but this is not sufficient. So the number of bits which are needed, or the minimum number of bits which are needed to define 7 unique values, will be equal to 3 bits. So 3 bits will define 8 possible values, but only we need 7. So for example, we assign red, okay, we can assign it uniquely the code 000. Orange, for example, can be 001. And finally, let us say violet will be 110. So these are the 7 colors of the rainbow. So 3 bits, as a minimum, we need 3 bits. If I use 4 bits, I can have up to 16 codes, but I don't really need 16. Now notice that I'm defining here, okay, only 7 codes, okay, for these 7 colors. There is actually 1 code which is unused because 3 bits will define 8 codes. 1 of them will be unused. Notice that the code 111 is not defined. It's not used, okay? That's fine. We can actually sometimes have, okay, extra codes that are not really used, not because we don't really have, we only have 7 elements in this case. We don't really have 8, but that's fine. So as a minimum, we need 3 bits, but 3 bits can define 8 codes, but we only need 7. So therefore, there is 1 code which is unused. Okay, is this clear? This is really the idea of coding. You assign a unique code to each element in this set. So here my set is a set of colors, and we have here 7 colors. So we need a 3-bit code. Okay, this is how we determine the number of bits for the code. If we had more than 8, let us say more than 8 colors, then I need more than 3 bits. Now, I could have done a different assignment. I could have started with red as 001 and violet as 111. This will mean that 000 will be unused. You could actually have a different assignment for these different colors. So this assignment is not unique. You can change it if you want. You can start at 1 and you can end at 7. 111 will be 7. And 000 can be unused. For example, we can use 000 to indicate black, for example. When you have the lack of any color, we can use it as 000. So we can actually come up with a different assignment. So this is just an example of an assignment where we assign to each color a 3-bit code. Okay? So this is called coding. If you have any question, interrupt me. Otherwise, I'm going to assume that you understand the topic. I'm going to move faster, okay, fast to the next slide, and so on. So the minimum number of bits, okay, the minimum number of bits which is required to encode, let us say, a set of elements. So here my set consists of M. M is the number of elements that I have in this set. So because we are going to represent each element with a binary code, so binary here, it means that the base is 2 or the radix is 2. We have to determine n. N here is defined such that m will be between 2 to the power n minus 1 and 2 to the power n. Notice that m is greater than 2 to the power n minus 1. So n minus 1 bits are not sufficient. And it is less than or equal to 2 to the power n. So that's how we define n. It must satisfy this inequality. Now, you can take here a look at n. You can calculate n as log base 2 of m, but you take the ceiling function. So here, when you put, so x here, this is the meaning of the ceiling function. Okay, so the ceiling function, it's the integer which is greater than or equal to x. So if log base 2 of m is not an integer, you have to look at the nearest integer, which is greater than or equal to x. Right, let me ask you this question. If I have 10 decimal digits and I would like to assign to them a binary code, okay, so let us do the encoding for digits, for the 10 decimal digits. How many bits do I need to represent 10 decimal digits in binary?
4.
4, yes. I cannot do it with 3 because 2 to the power 3 will be 8 digits, but I have 10. So therefore, I have to go to 4 bits. With 4 bits, I can represent 16 elements, but I only have here 10 digits. So I can represent with 4 bits, I can represent 16 digits, but in decimal, we only have 10. So therefore, we have to go with 4 bits. But there will be actually 6 digits, we have 6 codes, okay, binary codes that will be unused. So the answer here will be log base 2 of n. Log base 2 of 10, okay, is 3 point something. It's greater than 3, but less than 4. So we take the ceiling function, and therefore it becomes 4 bits. So we use 4 bits to represent 10 decimal digits, okay? So this is called coding. Now, in the past, okay, in the early days of computing, when people have invented computers, okay, they used binary because, as I said, that it's actually is a lot easier to design digital circuits that will use binary numbers, ones and zeros. For example, using high voltage and low voltage. Okay, I talked about this in my introduction. Okay, last week. So they faced the problem, how do we represent 10 decimal digits? So they decided to assign 4 bits to each decimal digit. So they invented decimal codes. So decimal codes, okay, so as we have seen that binary numbers is the most natural for computers, but people are used to the decimal number system. So therefore, people came up with the idea, why not to use binary to assign codes in binary to these decimal digits? These are called decimal codes. So we need actually 4-bit codes because a 3-bit will not be sufficient. We have 10 decimal digits, so therefore we need 4 bits. Okay, so with 4 bits, we can actually have 16 unique codes, combinations. Okay, of 4 bits, we can actually start from 0, 0, 0, 0 to 1, 1, 1, 1. Okay, so these are 16 unique values, but I only need 10 digits. So therefore, there will be 6 codes that will be unused. So 10 codes will be used for the 10 decimal digits, and 6 will be unused. Okay. Now, how do we assign the code to each digit? We can actually come up with different ways of doing it. For example, BCD means binary coded decimal. So we assign here to the decimal digit 0. We start at 0, 0, 0, 0, and we go all the way to 9, which is 1, 0, 0, 1. Now notice that this number in binary will be 9 in decimal. So basically, we assign to each decimal digit, we assign to it a unique, okay, BCD code, binary code. Okay. Now, we only have 10 digits. So there are 6 codes that will be unused, which are from 1010 to 1111. These are unused because we only have 10 decimal digits. And with 4 bits in binary, you can have 16 codes. So therefore, 16 minus 10 will be 6. So these 6 codes are unused. Now, we say that BCD is a weighted code. Now, notice that each bit has a weight. The most significant bit has a weight of 4, is a weight of 8, then 4, 2, 1. Okay, so when you look here at 1001, okay, the most significant one will be 8. This is 0, this is 0 plus 1. So 8 plus 1 will be 9. So we call it a weighted code. Okay, let us take a look at 7. 7 will be 0, 1. This one is 4 plus 2 plus 1 is equal to 7. Okay, so the code is weighted and the weights are 8, 4, 2, 1. So each bit has a weight. Okay, the least significant bit has a weight of 1. The most significant bit has a weight of 8 because we have only 4 bits. So we call it a weighted code. And there are 6 codes, okay, which are invalid. These are not really valid decimal digits. These are 1010 to 1111. Now, if you have the number 13 in decimal, then you can represent it with 2 BCD digits. So the 1 will be 0001, and the 3 will be 0011. Notice that this is the BCD representation. So each digit in decimal will be represented with 4 bits with a code, okay, with a BCD code. And the BCD code will consist of 4 bits. So if you have 2 digits in decimal, you have to represent them with 8 bits in BCD. Is this clear? This is the meaning of BCD. This is actually binary coded decimal. So we are using coding for the decimal digits. Now notice that this is different from conversion. Okay, so conversion is when we convert decimal to binary is different from coding. For example, when I have 13 in decimal, okay, we can convert it to binary as 1101. This is called conversion. So you can represent the entire number 13 in binary. Whereas coding, you take each digit in decimal and you code it in binary. So you code the 1 separately as 4 bits, 0001. And the 3, you can actually code it as 0011. So this is called BCD coding, okay? So you have to understand the difference between coding and conversion. Conversion, you look at the decimal number as just one number and you convert it to binary. Whereas in coding, you extract each digit, each decimal digit, and you code it in binary. So in the case of conversion, we got only 4 bits. In the case of coding, we got, for each digit, we got 4 bits. So we got 8 bits in total. So the number of if you have n decimal digits, if the number has n decimal digits, okay, and you would like to code it, then you need 4 times n, the number of bits in BCD. Whereas if you would like to convert it to decimal, you might actually get much less the number of bits. Okay. So there is a difference between converting the decimal number to binary and between coding it in BCD. Any question about this?
Doctor, can you back to slide 41, please?
Can I go backwards? Okay, this slide.
Yes, the weights are 842.
8421. Yes. So the most significant bit has a weight of 4, and the least significant bit has a weight of 1. It's just like, okay, converting it from decimal to binary, but we take it digit by digit. So for each decimal digit, we can represent it in BCD.
Yes.
Okay. Now, BCD is not the only code. We could actually have done different assignments. So BCD is just one assignment, one way to code the decimal digits in binary. There are other ways that people have invented. So BCD will start from 0000 and it will end at 1001. And the remaining six codes are unused because we only have 10 decimal digits. So people have thought that, okay, maybe if we have different codes, okay, if we use different weights, we might actually end up with different codes. So they came up with different ways to code the decimal digits from 0 to 9. For example, if we use 5421, now we give here, rather than giving 8 as the most significant bit, we give it 5. This is also a weighted code, but the most significant bit is 5. Now, when we have the number 5, okay, the first thing you have to do is that to assign 1 to the most significant bit. Although we could actually have encoded 5 differently as 101 here, like in BCD. In the case of the 5421, 5421 is not the 8421 BCD. So therefore, we start always with 1. So if the number is 5 to 9, we always assign 1 to the most significant bit, okay? Because the most significant bit has a weight of 5. So therefore, we start with 1 with the most significant bit, and then 6 becomes 1001. So this will be 5 plus 1, 7 will be 5 plus 2, 8 will be 5 plus 3, and 9 will be 5 plus 4. Okay? So this is a different way to assign the code to these decimal digits. So it's called 5421 code. This is just a third possibility is to use 2421. This is yet another way to assign the code, okay, to these 10 decimal digits. So notice that from 0 to 4, the first 5 decimal digits from 0 to 4 are identical, okay, in BCD 5421 and 2421. The difference is that when you reach 5, so when you reach 5, 5 is encoded as 1011. Now that's interesting because 1011, if you look at the weights, this will be 2 plus 2 plus 1. Okay. Again, we did not choose 101 because 101 will give you also 5, but they assign a different code. So 2421 will uniquely assign 1011. So this 1 is 2 plus 1 will give you the 5. If you would like to get 6, it will be 1100. So this is 2 plus 4 will give me the 6. And finally, 9 will be 1111, which is 2 plus 4 plus 2 plus 1 will give you the 9. So therefore, the weights are chosen so that their sum is equal to 9. Now that's an interesting code, okay, an interesting weighted code, okay. Now notice that, okay, it's a 2421 is self-complementary. In other words, if you look here at 4 and 5, 5 is the complement of 4. So you have 0, 1, 0, 0. Now, if you complement the bits, the 0 becomes the 1 and the 1 becomes a 0. You can see that 5 is the complement of 4. You just have to change the 0 to a 1 and change the 1 to a 0. Now, notice that 6 is the complement of 3. 3 is 0, 0, 1, 1. 6 is 1, 1, 0, 0. And finally, 9 is the complement of 0. So this is 0, 0, 0, 0, and this is 1, 1, 1, 1. So it's chosen in a clever way. The weights are chosen so that 5, 6, 7, 8, 9 are the complements of the digits above them. 5 is the complement of 4, 6 is the complement of 3, and finally 9 is the complement of 0. Okay? So basically, you just have to complement the bits. There is also another weighted code, which is 8, 4, -2, -1. In fact, you can choose the weights to be negative. Now, in the 2, 4, 2, 1, 5, 4, 2, 1, and BCD, all the weights are positive. But there is no reason why not actually making it negative. So if you choose a negative weight, okay, suppose I would like to have, let us say 1. Now, 1 will be represented as 4 minus 2 minus 1. So this will be 1. Whereas 2 will be 4 minus 2, and 3 will be 4 minus 1. And then you have 4, which is 0, 1, 0, 0. And then 5 will be 8 minus 2 minus 1, and so on. Notice that the 8, 4, -2, -1 is also self-complementary. Look at the bits, okay? The codes here for 5 and for 4. So if you complement 0, 1, 0, 0, you will get 1, 0, 1, 1. So notice that 5 is the complement of 4. And 6 is the complement of 3. And all the way here to 9, which is the complement of 0. One last coding system, or one last example, is the excess3 code. Okay, this is a different coding, okay, for the decimal digits. Notice that we take every decimal digit, we add to it +3. This is why it's called excess3. So we add +3 to the decimal digit. So 0 becomes 3, and we encode it in binary 0, 0, 1, 1. 1 becomes 4, so we encode it as 4. And finally, 9 plus 3 is 12, so we encode it as 1, 1, 0, 0 in binary. Now, excess3 is also self-complementary. Notice that 5 is just the complement of 4. So 4 now is 0, 1, 1, 1, and 5 is 1, 0, 0, 0. Okay, it is also self-complementary, but it's not weighted. It's not weighted. So unlike the first 4, they are weighted. Excess3 does not use weights. It just adds 3 to the digit. So 5 plus 3 is 8. It will be encoded as 1, 0, 0, 0. 4 plus 3 is equal to 7. It will be encoded as 7 in binary. Is this clear? So these are codes, decimal codes, that we can assign to the 10 decimal digits, and we have seen that there is more than one way to code the 10 decimal digits.
Doctor,
Fadal.
How the computer know how to distinguish between these codes, between these systems?
It's the software. Okay, it's not the hardware. It's the software. Okay, so for example, if you are using BCD in your program to represent the decimal digits, you as a software designer, you can actually tell, okay, the meaning of these bits. Or you can design a special circuit in the hardware that uses a special code. So for example, if you don't really want to do conversion, okay, sometimes circuit designers use a certain code to represent these 10 decimal digits. So you as a designer of this circuit, or if you are using software, you are writing the software, you can decide, okay, whether you would like to do, let us say, conversion, or you would like to use coding, and you give a meaning to the bits. So remember that the bits have no meaning. When you store bits inside the memory of a computer system, they have no meaning. Okay, it is us as a human beings or the software who is actually assigning. So if you're just storing bits, okay, you cannot tell what these bits actually mean. They can mean anything. Okay, so we use bits to represent integers, we use bits to represent fractions, We use bits to represent negative numbers. I'll talk about negative numbers later. We use bits to represent, let us say, characters, colors, and so on. So the software gives a meaning to these bits. Okay, I'm just giving you an idea here that how you can code, okay, the decimal digits in binary. Now, how you would like to use these codes, it's up to you. You can design a special circuit that will do the coding of the decimal digits. If you would like to avoid using binary, you would like to do, if you would like to, to avoid doing conversion to binary, you can actually use BCD codes. You can use codes. And there are different ways to assign the codes to these 10 decimal digits. Okay. One more example, which are the character codes. Okay, so what we have seen in the previous slides, okay, are codes which are assigned to the 10 decimal digits. How about characters? Okay, characters are not really are symbols. Okay, and okay, we need to assign codes, okay, for these characters. Not only that, but we have to standardize the use of these codes because the same characters have to be represented exactly the same way across all computers. Because let's suppose that you have a document on the internet and you download it on one computer system or another computer system, okay, the codes have to be represented exactly the same way on all computers. So there must be a standard. So people have invented standards for characters. For example, the ASCII. ASCII is a standard. It's the American Standard Code for Information Interchange. This is how they interchange text across different computer systems. So if you take, let us say, a text file and you store it in it characters and you would like to open it on another computer system, you should be able to read exactly the same characters. So they assign 7 bits, okay, to each character. So the original ASCII standard used 7-bit character codes, and these are numbered from 0 to 127, because with 7 bits, you can have 128 possible values in binary, and you can number them from 0 to 127. But then people have extended, okay, the ASCII to become 8 bits. So now we have 8-bit character codes, okay, so with 8 bits, you can have 256 possible characters. So we start at 0, we end at 255. But then 256 is not really sufficient to represent, let us say, all the characters of all languages around the world. Okay, so for example, to deal with Chinese, Japanese, and Korean, you have more than 256 characters. Okay, so these people have languages that have a large number of characters. In English, there are only 26 characters. You can actually have 26, okay, 26 letters. You can actually have 26 lowercase letters and 26 uppercase. And also you have some kind of special characters. Okay, let us say for a comma, for a period, semicolon, for parentheses, brackets, braces, curly braces, and so on. And the different operators like, let us say, addition, plus, minus, multiply, divide, and so on, slashes. So you have actually all sorts of symbols that you would like to assign to them codes. But then when you deal actually with Chinese and Korean and so on, they have more. So you cannot really fit it actually within an 8-bit character set. Okay, so 8 bits can only represent 256. You need 16 bits. If you use 16 bits, so the Unicode standard was introduced so that they unify the representation of characters, okay, around the world. Okay, so for all different characters, okay, it includes English, Latin, different characters, Chinese, Japanese, Arabic, and so on. Okay, so all of these characters are represented in Unicode, and they assign a unique code to each character. So it's called a universal character set. Okay, let me show you here the original, okay, 7-bit ASCII codes. These are called the printable ASCII codes. Okay, so space itself is a character. and it is shown here in hexadecimal. So notice that the columns here are numbered from 0 to F, where F here is 15, A is 10, B is 11, and so on. And we start here at 2 to 7. So if you would like to find the character code, okay, or the ASCII code for a given character, for example, 20 in hexadecimal will be space. If you converted 20 from hexadecimal to decimal, it will be 32 in decimal. 21 will be the exclamation mark, and so on. So we have different symbols. Okay, okay, all of these are called characters, and each one is assigned a unique code. So if you would like to find, for example, what is the code, okay, for the character A, for capital A, it is 41 in hexadecimal. So look at the row and the column here, okay, and join them. So 41 in hexadecimal, it will be 65 in decimal, and this will be a unique code for the character for capital A. For lowercase a, it is 61 in hexadecimal. Okay, so this was the initial ASCII code character set, and it is a standard. Okay, so all computer systems will follow the same standard, and this way you can interchange text files having these characters. But this was extended to 8 bits, and then it was extended to 16 bits to include actually many other characters, okay, including Arabic, different European languages, Russian, okay, as I said, Chinese, Japanese, and so on, Korean. All of these were added in the Unicode character set. Okay, is this clear? So whenever we are dealing with, let us say, symbols, okay, so this is a character set, and we have to assign to each character a code. So the code is a binary number which is stored inside the memory of a computer or inside a file. So basically the characters become digits, become numbers, become codes. Okay? Questions? Right, I'm done with this topic. Okay. I did not show you the control characters. So here row 0 and row 1 were not really shown. Each row can have 16 characters, okay, because we have 16 columns. I did not show you row 0 and row 1. These are the first 2 rows are reserved for control characters. So control characters are not really printable characters. You cannot actually print them on the screen. What they do is that they have special meaning. For example, character 0 is the null character. Okay, people use it in some programming languages, like in the C programming language, C, C++, and other programming languages. They terminate the string with a null character. So every string must be terminated with a null character. So it marks the end of the string. For example, character 9 will be the horizontal tab. Okay, you have a tab key on your keyboard, and it is represented by character 9. Okay, for example, character 0A in hexadecimal or 10 in decimal is the line feed. 0D, which is 13 in decimal, is the carriage return. So these control characters can control the movement of the cursor, okay, or they can actually mark the end of a line in a text file. So these are control characters, okay, because you can actually use these characters, okay, to control the movement of the cursor, or you can use them, okay, to mark the end, let us say, of a line in a text file. So every line must be terminated with a line feed, and sometimes they use line feed and carriage return, so 2 control characters to mark the end of each line. Anyways, these are called control characters. They are not really printed. You don't really see them, okay, in a file, but they are stored inside the file, okay? Right. So that's it about this presentation, okay? There is more here topic about parity and error detection codes. I'll come back to this topic later, okay, about parity generation and parity error detection, okay, but I'll skip it for now. There are only 2 slides here, so I'm going to skip it for now, and then I'll come back to it in a later presentation.